Good morning, good afternoon, good evening. Hello, guys. Thanks for checking in with this short video clip. It is pretty short regarding some examples of first order integrated rate law equations. From a previous video, we derived these based on the idea that a rate would be equal to some constant times the concentration of some species to the first power. So, whether or not you want to go back and review that, it's up to you, but they're useful equations. So take, let's see, e to the x on this side and e to the x on this side, and it rearranges to give that. And also this one for the half-life of first order equations, also nice many times. So let's just jump right into a few examples. First order decay of a reactant C begins with a concentration of 1.12 molar. The constant for that first order decay, 0.0052, 1 over molarity seconds. How much will we have left after 50 seconds? Well, I'm told quite a bit of info. I know an initial concentration. I know the constant that describes how quickly that concentration goes away. And I have a time. The time is 50 seconds. So as soon as they say first order, I think to myself, I wonder if I'll need this equation. Sure enough, one good way to do it is to put the constant in for k, put the t time in for t, 50 seconds, and the original or initial concentration of C is 1.12 molar. And do a little bit of math, a little bit of algebra. This is the natural log of C equals negative 0.147. To get rid of the natural logarithm on this side, I take e to the power x, and I'll take e to the power negative 0.147. And the ending concentration, 0.863. And does that make any sense? Let's see, I started at 1.12 and I go down to 0.863 in 50 seconds. That constant's pretty small, so it means it doesn't progress very quickly. I think that makes sense. Another way to solve that mathematically would be to use this equation, which is just a rearrangement, a mathematical rearrangement of this equation. And so I wrote that out as well if you wanted to look at it and see how indeed it does give you the same answer. Some folks like this one. They think it's more straightforward or more simple. This little caret is a common symbol on the calculator key for to the power. So that's e to the power x or e to the power negative kt. Alright, here's another interesting application. Most of the medicines we take are metabolized or decay away into something different in your body by a first order rate process. Who's to say what tissue or organ in the body metabolizes or decomposes that particular molecule? But in terms of time, the time it takes is sort of a first order process. Let's say some hypothetical person takes her daily medication, and let's say the constant for that decay over time is 0.75 1 over hours. Interesting. She takes 90 milligrams, and we're wondering how the pill that she takes that contains 90 milligrams of medication, how long will it take for that medication to drop to 53 milligrams? Well, it didn't just disappear. It looks like, 37 milligrams got changed into something different. And indeed, it would be hard to measure the total amount of chemical coursing through your tissues and blood vessels, but anyway, this approximation works pretty well. So again, if it was first order, I take my favorite equation for first order decay reactions. The storyline was she took a 90 milligram tablet. We're wondering how long will it take, how much time will it take for that 90 milligrams to decay into 53 milligrams. And the constant, 0.75, did I get that right? I did, 0.75 1 over hours. So the constant's in hours, and so my time will be in hours as well. Do a little bit of math, the natural log of 53. Oh, the natural log of 90. Oh, I forgot to mention, isn't this curious how our equation usually is references us to the molarity, but it also works with grams, gas pressures, various numbers of different descriptions of amounts of chemical or concentrations. And let's see, I'm trying to solve for t, so I subtract this 4.4998 from both sides and divide by negative 0.75. That negative is part of the equation, if you remember, it's right there. And the answer is about 7/10 of an hour. What's that? 50 minutes? No, it's 40 minutes? Something like that. Alright, one more. Interesting application of first order decay constants and equations. Most radioactive processes decay according to first order kinetics. We call it first order kinetics, decays. Here's a radioactive sample. I start with 37.5 milligrams of a radioisotope, and after 20 days I have 22.1 milligrams of this isotope, this nuclide remaining. What's the half-life of the isotope? That seems like a tricky question. It has several different steps. Let's look at it. Again, same equation. I start off with 37.5 milligrams of radioactive isotope. How long will it take to decay into 22.1 milligrams? Although you know the difference didn't just disappear from the universe, it got changed into something else. Well, when we see nuclear changes, we might hedge on that bet a little bit, but in any case, 20 days later. So the only thing I don't know is the constant. They told me this, they told me this, they told me this. What is the constant? And I solve mathematically fairly simply for the constant, 0.0264. Subtract this from this side over to this side, divide both sides by negative 20. The constant 0.0264, and my time was in days, so my constant will be in days as well. Well, I've almost answered the question. That's the constant of decay for this radioactive process. Then the half-life is 0.693 over K. And that half-life doesn't change for first-order decay processes. And this was 1 over days, and so the days flips to the numerator, and so my half-life time, the time it takes for half that substance to go away, 26.25 days. Oh yeah, here I said if you happen to have forgotten this equation, you could go back to the definition of half-life, and if you knew the constant was 0.0264, like we had determined earlier, then I could go back and say, well, the definition of half-life is the time it takes, this time, for my original concentration, original amount, to go to 1/2 of that original amount. So this 1/2 of initial concentration, the full concentration, the time is the half-life time. And if I know K, then I can put it in and do a little bit more algebra and solve, for the half-life. Still trying to solve for T here. This would be the A naught over A naught cancels the natural log of a half. I think that's 0.693. No, negative 0.693. Right. And I get this about the same answer as above. Maybe made a little rounding error somewhere. But in any case, that's all. Thanks, guys. Watch the next video when you get time on second order integrated equation examples.